Hi everybody, and welcome to the beginning of page 64. Okay, so we're going to introduce a new definition on this page here, and you might recognize this as sort of formalizing something that we talked about earlier in the chapter. Okay, so let's read through this together. So let beta be an ordered basis for an n-dimensional vector space V over a field. We're going to talk about something called the standard representation of V with respect to our basis. Okay, what's the standard representation? Well, it's a function that goes from our vector space V to Fn. Okay, Fn is just a set of n tuples, okay, scalars. And here's how that standard representation is defined. Phi beta of x equals bracket x of beta. Okay, you remember what this notation over here represents? That's just the coordinate vector of x relative to our basis beta. So in a nutshell, what this function does is it takes a vector in our vector space V and it spits out the coordinate vector relative to whatever our basis is. Okay, and it turns out that this phi beta that we just defined as an isomorphism, there's a natural correspondence between the vector space and coordinate vectors relative to a basis. Okay, now the best way to get a feel for what this function is doing is just to look at some examples. Okay, so let's read example 5 together here. So they'd like us to let W be the subspace of all symmetric 2x2 matrices with entries in R. Okay, now recall that we have kind of a nice basis for the set of symmetric matrices that looks like this. We can build any symmetric matrix as a linear combination of those three matrices. Okay, so with that introduction, they'd like us to do two calculations here, starting with phi beta of 1, 2, 2, 3. Okay, what is that really asking us to calculate here? Well, phi beta takes the matrix and maps it to its coordinate vector. So we're simply asking the question, how do we build 1, 2, 2, 3 as a linear combination of our basis vectors? All right, well, looking at our basis, it's a nice basis. It's got lots of zeros in it, so it's not too difficult to figure out how we would build it. We just need to take 1 times our first basis vector plus 2 times our second basis vector plus 3 times our third basis vector. And the coordinate vector is going to be the tuple that we get. Okay, if we take our three coefficients and put those as the number in our tuple. Okay, so what we get then is the standard representation of 1, 2, 2, 3 is just going to be the 3 tuple that consists of these three coefficients, 1, 2, and 3. Okay, that's all there is to it. Okay, and then phi beta of 1, 0, 0, 5, same idea. You would simply ask, how do we build 1, 0, 0, 5 as a linear combination of these three vectors? And that's going to be a very similar calculation. Okay, phi beta of 1, 0, 0, 5 is going to be the coordinate vector 1, 0, 5. You can check that, okay, and confirm that 1, 0, 5 are the right coefficients to build this matrix. Okay, so I think we've answered the two questions in example 5. Let's do one more example just to make sure that we understand this. This is kind of getting used to notation, basically. Okay, so in example 6 here, they're giving us the vector space V equals P2 of R. Okay, and the standard basis for that looks like 1x and x squared. We'll call that gamma. The first thing that they'd like us to calculate is phi gamma of x squared plus 2x minus 4. And again, calculating that standard representation is all about asking, how do we build x squared plus 2x minus 4 as a linear combination of our basis vectors? Okay, well, let's see. Okay, so x squared plus 2x minus 4, it's like trying to fill in the blanks here. Okay, and you can see that we need to fill in the blanks by putting a -4 here, a 2 here, and a 1 there. Okay, it's all about those three numbers. And so therefore, the standard representation of x squared plus 2x minus 4 is just the 3 tuple that consists of those coefficients that we circled. All right, so we have just done the first of the two calculations. The second one over here is a little more interesting. Okay, so now they'd like us to calculate phi gamma inverse of 1, 2, 3. Okay, so we're talking about the inverse of the standard representation function. Okay, well, if the standard representation function takes a vector to its coordinate vector, then the inverse does the opposite. And so it's going to take a coordinate vector 1, 2, 3, and we're asking what polynomial would that map back to? Okay, well, we can analyze that by first asking what polynomial does the coordinate vector 1, 2, 3 build? Well, let's see. If we take 1 as the coefficient of our first basis vector, 2 as the coefficient of the second one, and 3 as the coefficient of the third, the polynomial that we build is 1 plus 2x plus 3x squared. Okay. Note that the calculation that we just did illustrates the fact that the coordinate vector of 1 plus 2x plus 3x squared relative to our basis, okay, is the tuple 1, 2, 3. And therefore, if we think about how this function is working, phi gamma inverse is going to take that coordinate vector 1, 2, 3 and map it back to the polynomial that coordinate vector builds. So 1 plus 2x plus 3x squared should be our answer here. Okay, we did two calculations, so let's maybe emphasize those. So one of them looked like this, okay, and the other one looked like this.